Eric,
Hey,
are you going to post a asynchronous lab for today for group two?
um, I am. What I was actually thinking about doing is starting the exam. Oh, I'm recording. I need to record. Okay, guys. So pre-recorded assignment, lecture, whatever. I've got my camera turned off because I'm using my laptop as a tablet entirely, so it's flipped over, which means that you'd just be looking at the ceiling and occasionally my bald head would pop into the screen. So that's not going to work. Since it's pre-recorded, you probably don't need to see me and I'm not going to see you. So I'll try to keep this as lively as possible without my beautiful face in the picture for you. Last time we started talking about reflection, transmission, and refraction. Well, we really didn't get into refraction, and heck, we really didn't get into transmission, but we did talk about reflection a bit. Now, diagnostic ultrasound is all about reflection or scattering, but in any case, echoes have to reflect back to us in order for us to see them. Determine if tissue interface reflects sound, or what percentage of sound is reflected by an interface. We need to know the impedance. Capital Z is the symbol for impedance. It's acoustic resistance. How much sound is impeded by the tissue? Interestingly enough, light does the same thing. Light, it's a very different type of wave, but it's a wave just the same. And we can see critical angles of light where, maybe I'll find a video and just attach this somehow. But it's an interesting video. If you take a flashlight under the water, here I'll put a little tiny flashlight. Oh gosh, my pen size is too small. Let me make that a little smaller. Pen anyway. You take a flashlight and you shine a light, and it hits a critical angle. There's an angle at which 100% of the light reflects, and so rather than the beam continuing out of the water, it will simply stay inside of the water and reflect. And so light does a very similar thing. But we're talking about sound, aren't we? So Z, impedance, is in rails. Now rails is kind of a funny number. It's, a typical impedance is like 1.6 million rails. So we have a very large number for that. And that is found by density. This is the Greek letter, rho, times the speed of sound in that tissue. So the density of the tissue times the speed of sound in the tissue is our rails. And so down here we had the loudest animal on the planet, a blue whale, not far from the shore, and he's yelling his head off. Well, how is that in the? Anyway, I'm thinking of Dory from Finding Nemo. Anyway, he yells. He's making incredible amounts of noise. This is like airliner type noise. Very, very loud animal. We don't hear a thing on the shore because all the sound is reflected. Why? Because the impedance down here is very different than the impedance up here in the air. Why? Well, actually, there's a huge difference in velocity and in density. So, very different impedances, whatever. Very different impedances. And that's important to know. If they are similar impedances, the sound will transmit from one tissue, or in this case, water to air, if for some reason they have a similar impedance, which they don't. Actually, coming back to light, great example. I wish I thought of this earlier. When you wear swim goggles, there's a little nose, and these are goggles. And little eyeballs in there. Okay. Goggles, the reason why they work. Think about this. You evolved, or were created. I really don't care which you prefer. For now, we'll just say you evolved. You evolved to live on this planet in air. Your eyes, the liquid in your eyes, the lens in your eye is a certain impedance, and there's got to be a way for light to travel through, and it does, of course, but when you wear goggles, you're keeping that natural impedance mismatch. The impedance mismatch, when I say a mismatch, what I'm really saying, the different impedance. You have your body, your eyeballs expect a certain impedance mismatch between the air and your eyes. And so when you wear goggles, it actually maintains that, that normal impedance mismatch. There's also another factor, probably actually more important when wearing goggles, and that is refraction. Refraction is going to be very important when you wear goggles. All right, let's move on here. So, and we're going to talk more about impedance going forward. We're not really done with it, but important, let me say again, impedance tells us if and how much reflection there will be at a tissue boundary. Actually, let's use my little squiggly here. If impedance, let's see, we're going to call this Z1 and Z2. If the impedance is very similar, or let's say the Z is the same, S-A-M-E, looks like an M or an S-A-M, the same, or close to almost the same, sound will travel through and it won't reflect at all, which is the same thing as saying this interface is invisible to us. We cannot see this interface if the Z is the same. If it's a little bit different, then sound will come to this point, a little bit will reflect back, and then much of it will continue on. But that little reflection is all the difference in the world. Now, we can see this. That is it produces an echo. Whereas this one over here, since the Z1 was equal to Z2, this was invisible. In other words, no echo. Where's the echo there? So if we can create an echo, we see it. If the Z is very different, then sound comes down and a very strong echo goes through, and little, if anything, continues on. Little, or if anything, continues on. But at this point, it really doesn't matter. Now we have a very echogenic interface. Why? When the echo is super strong, it is echo forming, echogenic. That's all well and good, except for the fact that now you have little, if anything, traveling through. And by the way, even if there is a little bit traveling through, that still has to come, any echoes produced still have to come back through this interface. And then you end up with an even smaller, so very echogenic structures basically create an acoustic shadow. It's basically an acoustic no man's land where no information is available to us because so much reflected right off of the interface itself. So this is called a high mismatch, a low mismatch, and invisible is no mismatch. All right, so everything has to do with mismatching impedances. All right, let's see, where am I now? I am going to erase a little bit here because it's just going to be hard to look at in the near future. Okay. Okay. I believe the book now jumps into incidence. That doesn't mean we're done with impedance, but we do have to talk about how sound comes to a interface. Let's see this, oops. This line right here, I'm kind of going to do that again. We're just going to call that a interface. And we can even put Z1 and Z2 down here. But all we're talking about, we're really not talking about impedance at the moment, we're talking about incidence, so let's just talk about that. Okay, so one direction, this could be coming in. As the sound's coming in this direction, it hits the interface at an acute angle. Acute is less than 90s, less than 90 degrees. We could jump over to the other side. This one is coming in from another direction. That is an obtuse angle, greater than 90 degrees. And if you really look at it, is there, in our case, does it really matter whether we're talking about a obtuse or acute? It really doesn't. The sound's coming in at an angle. That's all we care about. So we can call both of them oblique angles because they're both oblique. Oblique is anything that is not 90. Not 90-degree angle. All right, so we don't use the terms acute and obtuse very often. We will say oblique more often. And then our third possibility is that the sound comes straight down at the tissue interface. That is called, well, a 90-degree angle, a right angle. It's also called normal, the normal. Sometimes the normal is just like a dotted line against an interface, and the dotted line represents the normal, or the 90 degrees. Perpendicular, as opposed to parallel, perpendicular is 90 degrees, and orthogonal. Orthogonal, I remember at least one of your tests uses the word orthogonal, and that messes people up. So I want you to remember orthogonal, perpendicular, normal, right angle, 90 degrees all mean the same thing. Ah, yes, and this is how normal people draw an interface because that's just mathematically the X and Y axis. That's how normal people do it. But Edelman is not normal. But this is important to know. It's important to be able to realize that this is the same as this. Exact same thing. I guess I can't say exact same thing, but it's the same thing. Let's get some of this ugliness out of here. All right. So once again, just, obtuse, and 90. This causes a little more confusion in the future, and I want to start tackling that now so that we understand where the confusion is coming from and hopefully get ahead of it so you don't get confused. But in any case, obviously incidents can occur in any of these ways. By the way, different things happen with different incidences. Let's say this interface is a relatively shiny echogenic interface. Why can't I think of the specular reflector? If this is more of a specular reflector, we can imagine that this sound wave is traveling in 90-degree angle, and guess what? The energy is going to come. What doesn't continue on, the energy is going to bounce right back. This is why I say in grayscale, when we look at the CCA, there's actually nothing wrong. In fact, it's really good when we have our CCA flat on the screen. That's because we kind of want those 90-degree angles. And that just produces a lot of reflection. And so that's good. And of course, some goes through and more reflection there, and some goes through again. And, maybe the spine reflects over here. But 90 degrees or orthogonal is good for grayscale. Color Doppler or spectral Doppler is different. We don't want a 90-degree angle, but that's completely different concept entirely. Okay, so this is how it draws. Let's move. Moving on. Moving right along. Okay. So I kind of mentioned up here, I erased it already. I drew a little, well, what I did is I drew a carotid here, right? And I drew an arrow here and an arrow there, and then an arrow here, and then a smaller arrow there, and an arrow here, and then maybe a small arrow. And all the arrows going down are the beam, and all the arrows going back up are the echo. Remember, this is what we see. We see echoes. Gotta have echoes. Without echoes, we are just simply rubbing people down with transducers for no reason. Okay. Incident and reflected intensities. Incident sound. Now, I think I erased some information. That's all right. Well, tis what it is. The size of the arrow and also the depth of color represent the strength. So remember, attenuation coefficient, we could be losing, I'm just going to put this, that's an about typical, what was it? Almost 3 decibels per centimeter average. Remember, that's the same as saying 1/2 or -1/2 because we're losing half of our energy every centimeter, more or less. Remember, it depends on frequency. It's actually frequency divided by 2. Anyway, so this indicates here that we have a certain intensity. The incident sound intensity in watts per centimeter squared is whatever it is. Let's just, for the heck of it, we'll throw some easy numbers in here. And we'll say, well, let's make it 200. 200 watts per centimeter. It comes down a little bit. It loses half of that. So then it's 100. So by the time it reaches tissue 2, we're down to 100 watts per centimeter. It keeps going, and let's say it's tissue number 3, that's 50. Remember, we're losing half every centimeter. Now, obviously, guys, I'm just making up numbers. Tissue 4, 25. And then beyond that, we're going to be, half of 25, 12, let's say, or 12 and a half. Let's just say 12. And that's basically, I'm trying to represent the weakening of the sound beam, and it happens very quickly. Then we have reflected sound intensity. And so the reflected that's getting weaker and weaker as well every time we go through from one tissue to the next. Well, of course it's getting weaker. The incident sound is weaker. If that's weaker, the incident beam is weaker, then the echo is of course going to be weaker as well. Now the machine, by the way, knows this and adjusts for this, all right? The engineers figured this all out. They made an adjustment. In fact, what they did is they have a, let's call it a constant TGC. Remember those TGCs? Those are those little, on our machines, they're electronic, so you pull them up and you can sweep them so that they're, they slip to the side. That basically, that's augmenting a TGC that's already built into the system. Time gain compensation. In other words, the machine understands that for every centimeter of depth, it has to listen harder for the sound. If it doesn't listen harder, then what you will end out having is a screen that's very bright at the top and very dark at the bottom. And that doesn't do us any good. We want more or less the same brightness from top to the bottom. It doesn't always work out that way, which is why we have control of TGCs as well. So we can change what was already built into the computer. We could augment it to better suit our exam at that time. Let's see. What else did I write down here? Yeah, okay. A little math. This is easy though. This is super, makes sense. Conservation of energy. Assume, oops, that was the wrong pen. Assume no energy lost. Conservation of energy applies here. So in other words, the incident energy is equal to the reflected times the transmitted. Let's get this little picture here. Dang it, go away. Oh my God. All right. Incident Intensity, that is this guy here. And I don't know if you could see that. I put a 100. Here, I'll write it again over here. That's 100%. 100%. Now I'm not talking about watts. I'm just talking about 100% of whatever it is. 5 watts, 1,000 watts, I don't care. It's 100%. As it hits this interface, a certain amount is reflected. Myself a little more room to write. Certain amount is reflected, and another certain amount is transmitted. Now, I'm not sure why I drew it like this, because actually the reflected is normally in normal biological tissue. The reflected sound is much smaller than the transmitted. And the way I drew these arrows, I actually drew the arrows so that this reflected sound is very strong compared to the transmitted. If this were the case, let's just say reflected, let's say that that's 75%. And only 25% is transmitted. That is not a normal situation. Well, it might be normal if this were bone. You see, there's a huge impedance difference between soft tissue and bone. By the way, this is the weird thing. There's also a huge impedance difference between soft tissue and lung. So kind of weird. Both a very stiff, dense material versus a very spongy, the opposite of dense, why can't I think? Low bulk module, whatever. Extremely low density material. They both have the same effect of reflecting a lot of sound. So what does that mean? Very strong echo. In other words, echogenic. 25% transmitted, that's really bad for us. We don't see anything, really. And that's why we typically don't image bone and don't image lung, or at least as much as we could try to, but we don't see into it very well at all. A little more typical, I'll just give you typical numbers, although I'm not going to change the arrows. Make sure a little smaller so I don't. Whoops, no. A little more typical is more like reflected 1%. Only 1% is a typical interface, which means transmitted 99%. This would produce an echo, but it'd be weak. A weak echo. In other words, this would be a hypoechoic or we'll just call it hypoechoic. Certainly not echogenic. I don't really like the term hypoechoic here because that's a relative term. And we need to see everything else, whereas echogenic is a little more of an absolute term. But hypoechoic is the best word I could use right now. In other words, weak echoes. It might be just a darker gray on your screen. Okay, so back over to here, this green here, 100% equals intensity reflection coefficient, ooh, that sounds scary, plus intensity transmission coefficient. When we say 100%, we really mean incident. Incident beam is always considered 100%. But this makes sense though. We're just saying that over, like when you come back over here, this is 100%. And assuming no energy loss, of course, it's a difference between, well, it's the sum of transmitted and reflected. All right, I might have to pause this because I don't think I have. Oh, I got to there. I am still going to have a pause though, because I don't even have my book next to me. Let's zoom in a little bit on my awesome little interface here. I was recording. Okay. So I don't have a lot of stuff pre-written, so which is fine. The only problem is that you're going to hear constantly. Okay. We're going to talk about reflection with normal incidence. So there's going to be an equation. This is probably the scariest equation that you'll see, and it's really not that bad. It's actually not that bad at all. It technically only works with normal incidence because once you get into obtuse incidence, there are so many variables that it cannot be accounted for. So this is, well, anyway, going forward, right here, reflection with normal incidence. This is called normal. We have two tissues. We have tissue 1, tissue 2. Tissue 1 is going to have its own impedance, so that's Z1 and Z2. Now, what I've already drawn here is obviously my baseline, or not baseline, my tissue interface, and the incident beam is up here, of course. That is our incident beam. And I've drawn a reflection. So that's our reflected echo, or reflected intensity. I've made it smaller than the transmitted. So reflected, transmitted. So I know from this picture, if I've drawn it, somewhat correctly, I know that there is a impedance mismatch. So, is there a mismatch? Mismatched Z question, yes. Because there's an echo. So, yes. If there were no echo, that Z1 and Z2 are equal. Is it high, this impedance mismatch? Well, the way I've drawn this, I'm going to say no. Because we'll go ahead and just say that this is 1%. And then this one was 99%. That might not be accurate as far as my picture is concerned, but you get the idea. The weakest link here is this echo here is very small compared to the incident and transmitted beams. So mismatch is a low impedance mismatch. Yes, because of this, we have a small echo returning. So calculating this, so we mentioned earlier the intensity reflection coefficient. Oh, sounds horrible, right? It's not a big deal. Seriously, guys. Simply put, whoops. We're going to take Z2, and by the way, you have to be given Z. Can you calculate Z? Sure. If you know rho and the speed of sound, then you can calculate Z. But I don't think anyone's ever going to ask you to do that. So this is going to be a given information. If you are asked to find this, you will be given this information. So let's see, IRC Z2. Oh, let's see, that was Z2 minus Z1 squared. Oop, let me draw this slightly differently. Kind of screwed that up a little bit. And that's important because it's the whole thing is squared. And then down here is simply Z2 plus Z1. Whatever that is, you multiply by 100, and that's going to give you your coefficient. Reflection coefficient in normal tissue, that's going to be, I'm going to put low. A low number, small number. The intensity transmission coefficient is, well, that's easy enough. The intensity transmission coefficient, once again in percentage, is simply the transmitted divided by the incident. Now you guys might be looking at this up here thinking, wait a minute, there should be another way. There is. There is. So transmission coefficient, that's going to usually be a high or a large number. So the other way, another obvious way of looking at this, these are basically they're reciprocals, right? So the other way of saying this is 1 minus the intensity reflection coefficient. Intensity reflection coefficient. That's what your book says, but it really should be 1 times 100, right? Because we're looking for a percentage. So your book doesn't say the times 100 part. Unless I'm losing my mind, it would seem to me that would be the way to do that. Given what we have just learned about reflection, it's really simply a value of percentage. Since 100% of the beam intensity must be accounted for, the percentage of words, conservation of energy at the boundary and clinical environment. Clinical ultrasonic imaging, 1% or less of the incident sonic beam, sound beam is reflected at the soft tissue boundary. That's important, soft tissue. Not soft tissue, hard tissue, then that's a very different number. Thus, over 99% of the intensity it's transmitted. And so that's what I tried to illustrate. Where's my, oh, there we are. So I'm trying to illustrate here that each time this is like 1% and 1% and 1% and 1% and so on. That's typical soft tissue. Ugh, whatever. Okay. Let's see. I'm starting to write too large, and I'll just use half my page here. Well, darn it. All right, and there's more than one way to skin a cat here. Let me just take everything I just did. That way it's still available for me to go back to, but it's no longer in our way. So, reflection and transmission with oblique. Okie dokie. So, we're going to get into page 98 in your book, reflection with oblique, but that also, we're going to talk about transmission. Now, once again, in the book, the way he draws it, I don't know why he does it this way. He draws the boundary layer like that, and the incident beam going in like that, and then bouncing off. And so, but that, I don't know why. I don't know why he feels the need to mess with us like that. I really prefer drawing it horizontal. So let's go ahead and do that. I really made this. Okay. So let's just get our interface here. That was an eraser apparently. Do that one more time. Okay, we have an interface. We have a normal. So I'm going to draw in normal. That doesn't mean the beam's hitting us at a normal. I'm just drawing in a normal. In other words, a dotted line to create a normal. So that's going to be like, all right. Oh, let's get a pretty color here. And let's come in at an angle like so, which means the beam's traveling down. There's my incident sound pulse of sound, because we are dealing with pulses, right? So here's a question for you guys. I think we could all agree that this is going to reflect more or less like that, right? And we'll go ahead and draw there, and there's our pulses going away. Reflected intensity. While you guys are watching this, just answer yourselves. Now I could choose this angle here, but I think we're going to go off the normal. And this could be why. So this could be why he draws his. Oh, hey Emily. So I don't know if you received the email. I'm just going on pretty much on my own. You're more welcome to stay here and watch and ask questions, but I'm on my own right now because I wanted to get a full lecture in. We didn't have time. Anyhow, so we have two. Let's get another color in here. We have two angles off the normal here. And I think I was just saying, I think this is why he writes he draws this sideways because he's taking his measurement off the normal, and so maybe he feels that that's better, and I get it. But in any case, this is my theta, and that's just a way of saying an angle. Theta I for incident. And then over here is theta R for reflected. Now, if you guys are, oh, bye, Emily. Oh, hi, Gene. Or John, damn it, do that every time. So John, I don't know if you got my email. You don't have to be here right now, but you're more than welcome to be. Okay. Yeah. So my incident angle, reflected angle. If you think about this, guys, if I'm going to use a laser beam on a mirror, it's the same thing. These guys are always going to equal each other. Incident equals IR. Whoops, reflected R. So both these angles are the same. 35 and 35, 40 and 40, 20 and 20. They're always going to be the same. Grazing angle, Bobby, I'm a very small 100%. Weak incidence, however, reflections made. Similarly, when the sound beam strikes a boundary, no simple rules describe the process. No simple rules describe the process of reflection and transmission. Okay. Page 100, reflected angle always is equal to the incident angle. So I've already drawn that angle. Transmission. Okay, this is where it gets fun. Let's use another color here. I could have a transmission of, maybe let's do it like this. Have an angle coming down like that. Or I could have a transmission angle that does more like this. Whoops. First of all, let's use a different color. Yellow. Okay. Both of these transmission angles are possible. Actually, I'll give you a third possibility, and I'll go back to my original green. And I'm actually going to start up here. That's a possibility. So all three of these transmission angles are a possibility. Now, I want this to really seep in. Whether or not the sound reflects 100% or reflects a smaller number, and instead most of the, so let's say most of the sound beam travels through, that's impedance. We've already talked about impedance. What we're going to talk about now is refraction. Refraction, impedance had to do with rho times the speed of sound. Density of the tissue times the speed of sound is impedance. That tells you whether it reflects or not, how much is transmitted, how much is reflected. That's what impedance tells you. This is different. Students have a really hard time remembering or understanding that this is different, and so I just want to really put that down there. I have three different possible angles here. We have an angle here, theta t for transmitted. I have another possible angle from here to here. That's also another theta t. And then I have that whole angle there. That's a theta t. So we don't know which, only one of these is going to happen. It's not all three are going to happen at the same time. It's not a prism. This pretty much entirely has to do with only the speed of sound. So speed of sound, and also, just so you know, same thing happens with the speed of light. This is how a prism works. Or I don't want to say prism because that breaks the different light frequencies up, and that confuses the issue. This is just how refraction. Actually, you have a picture on page 101 of a pencil inside of sitting inside of a glass filled with water, and the pencil appears to be broken, right? It doesn't match up together, and that is because, of course, there is refraction going on. The speed of light changes in both the glass and the water, and that's what causes this refraction. Refraction, by the way, is probably not our friend. It can cause confusing images. Let me just erase a bunch of this. Okay, we'll just stick with this one. Okay. Now I have a mnemonic that usually works. It depends on how you draw your picture, but it usually works. Actually, it does always work, but the picture, the way I draw the picture doesn't always work, but mathematically it always works. And the mnemonic, let's see, let's do yellow. Speed up. Slow down. If the speed of sound increases in tissue 2, it will be fracted, it will refract away from the normal. Remember, that is our normal. Beam comes in at an angle, it goes away from the normal. So speed up, that theta t is larger than theta incident. You see how this angle is larger than this angle, okay? Slow down, theta t is smaller than theta incident. Different color. You can see that this angle here is not quite as big as this angle here, so it slows down. Now, the way I drew the picture, it also goes down or speeds up. It's just that if you draw the picture in different ways, that doesn't always work. But mathematically, theta slow down, theta transmitted is smaller than theta incident. And of course, the opposite is true, speed up. Ah, gosh, Snell's law. Smelly Melly. Snell's law. I hate Snell's law. I don't hate it. It's just like, why do we have to learn it? Because it just brings in a mathematical term that we're not really using otherwise, and so it doesn't really behoove us. But the sign, so this refraction of light, sound, well, light too, but this refraction of sound follows Snell's law. Oh, and there's also Kurt's law. Kurt's law. We'll get back to that one. So the sign, and that's something, that's the part. It's like, why do we really need that? We really need to add that to our repertoire right now. Sine of theta t. Your book says transmission angle, but that's what it is, theta t, right? Let's go back. Sine of theta t, all right, is, divided by the sine of theta I for incident angle is about equal, the ratio is equal anyway, of the, speed of sound. I'm just going to put C medium 2, and the speed of sound C in medium 1. What does sine mean? Page 102. The term sine may be new to you, right? Exactly, so why are we talking about it? A sine is a unitless number with a value between 0 to 1. The sine of an angle is derived from the mathematical theory of angles called trigonometry. The actual derivation is beyond the scope of this book, no kidding. Although calculating Snell's law is not required, it's important to understand the concepts of refraction. So he even says calculating this using sine is not important. So that's just kind of like, hey, heads up, this is what Snell's law is. And by the way, I wrote in my book anyway, just a little, just so you know, 0 degrees, an angle of 0 degrees has a sine of, whoops, got that exactly backwards, 0.0. 45 is a sine of 0.173. And you know what, I'll skip a couple and just go down to 90 degrees, which is the largest angle that we're going to deal with sine 1.0. So it goes from 0 to 90. The sine is 0 to 1. Other than that, don't worry about it. Oh, Kurt's law, though. Kurt's law is actually useful. Snell's law, who's that guy? Just some mathematician. But Kurt's law is actually useful. If I can remember Kurt's law. every 1% change in speed there is about 1% change in angle. This is Kurt's law. So, in other words, it seems pretty obvious, but if there's a 1% difference between the speed up here and the speed down here, then this theta angle is going to be very small. Or this, the change in direction is going to be very small. It's only going to be 1%. If it's a 10% change in speed, then there's a 10% change in the angle. And knowing that the speed of sound does change in different tissues, it doesn't generally change that much. Refraction is usually not a terrible problem for us. It can cause problems though, and undoubtedly we'll be able to see that in lab. I did forget to mention one thing. We never really mentioned this green line. That green transmitted line, it's perfectly in line, isn't it? Goes from up here, does not change course. It transmits, we know there's an impedance difference, but the speed of sound speed is the same. Speed of sound does not change. So let's go back to this then. What does that possibly mean? Well, the density must have changed, but this between Z1 and Z2, otherwise there wouldn't be transmission. I'm sorry, I just said that wrong. Back up. Boop, boop, boop. Yeah, it could be that the speed of sound is the same in tissue 1 and tissue 2 with a different density, in which case there would be a reflection, but it's also a transmission as well. That is correct. Got to be careful how I say these things. Awesome. We're done with this chapter. Let me just say one more time. Everyone or almost everyone has a problem with this. Let me just zoom in. Z. Zorro. Does it reflect? C. Speed of sound. Does it refract? Obviously, they're somewhat related, but this is really, it's an important distinction. Speed of sound Speed of light tells you whether or not something refracts. Z tells you whether or not something reflects. You know, you know what, I'm going to find a video. I'm going to write this down. Video refraction. And I'll make that the next asynchronous assignment I want you guys to look at. It'll be an easy video. It basically shows how waves refract when going from one medium to another. And hopefully it'll make more sense and kind of understand why it happens. It just helps, although it's not necessary to pass the SBI. Okay, so next one, range equation. We've mentioned that before. We've talked about how we count seconds between the lightning bolt and the sound, the thunder. That's using the range equation. So that's chapter 7. Chapter 7 is really short though. So next time we'll talk about probably chapter 7 and then get into transducers. That's definitely a longer talk though, transducers. All right. So remember, this is part of your asynchronous assignment. On your day, for instance, John, you are sitting there watching this right now. Just do me a favor and on, God, what day? Wednesday? I think, yeah, Wednesday, just get into the assignment and write done since I know you've watched at least part of this lecture. So this is your asynchronous assignment. All right. Adios.
Thank you.
Oh, Amy's there too. How many are you there?
Oh,
There's
sorry.
a few of you. There's a few of you. I have, by the way, I have my camera turned off because I'm just using this as a whatchamacallit, tablet. And so you'd just be looking at the ceiling and occasionally the top of my bald head. So I'm like, forget this.
17.
All right. And bye-bye.